So welcome everyone, and thanks for joining us at various locations around the world. And I'm very pleased to introduce our speaker today, Shun-Jen Cheng, who's at the Academia Sinica in Taipei. And he's going to talk to us about representation theory of exceptional Lie superalgebras.
Okay, thank you very much. Thank you very much for the invitation. So I was told by Anthony that this talk is supposed to have two parts. So the first part is because there are many graduate students that I should say a few, give a little bit of introduction to the subject. So I've first give an outline of this talk. So that's the outline of the talk. The first part. So what I will do is I will talk about so even starting out not in the superalgebra, but starting out with what simple, as we call what simple Lie algebras are and their classifications. And this will be very brief, and I will move on to simple Lie superalgebras and give a very rough sketch of their classification, but I will give all the examples of simple Lie superalgebras essentially. And the third part of the first part will be, I will talk about representation theory of Lie superalgebras. And so this is divided into two other parts. So part one is on finite-dimensional modular category. And then the second part will be on this so-called BGG category O. So this should, I hope to finish this in the first 40 minutes. And then I'll move on to the second part, part two. This will be about the main topic of this talk, about exceptional Lie superalgebras. So I will introduce first what the exceptional Lie superalgebras are. And then I will talk about the representation theory of these exceptional Lie superalgebras. I mean, there are actually, so there are three, I can share three of them, but this talk will only be about the representation theory of two of them. I mean, one of them is called this one parameter family D21 zeta, where zeta is a parameter, it's a complex parameter not equal to 0 or -1. And the other one will be about this so-called G3. And if you don't know what they are, it doesn't matter. I will describe them so as much detail as possible. Okay, so this is the outline of the talk. So let's start then with part one. So we'll start right now. So this is about so simple Lie algebras or Lie algebras in general. So I will give a quick definition. So you start with so first of all, today's talk so everything is over C. So G is, so start with what definition of Lie algebras is a vector space, and it has a bilinear map G cross G to G, and it satisfies these two famous identities. One of them is skew symmetry, and the other one is so-called this Jacobi identity. So this is just let me see. Yeah, see. So here X, Y, and Z are elements of vector space G, and so this is then definition of the algebra, and the example I will give also an example. So you take a V, this will be a vector space, so over C of course, and then GLV, so it's a set or a space. This is the space of linear maps from V to itself, and then you can define a bracket splitting operation using this anti-commutator, and then this will be a Lie algebra. So this is GLV. This is so-called general linear Lie algebra, and I should also mention a little bit about representation. So then representation, so if you have a G, which is a Lie algebra, then a representation of G. So this is a pair pi V. So where V is a vector space, and pi from G to GLV. So this is a homomorphism of the algebra. So it preserves the bracket. And so the example, so GLV, oops, sorry. So this GLV acts on V. So V is therefore, V is a GLV module or a representation. So yeah, as usual, so representations is the same as modules. Okay. So let me also quickly let me recall so the classification of simple Lie algebras, finite dimensional. So I do this because I want to make the analogy with superalgebra, the classifications there. So here the list consists of this classical Lie algebras, types A, B, C, D, and then you have the exceptionals. So you have this G2, F4, and you have the E families. So let me just for completeness sake. So type A, this is called this SLV. So these are a subalgebra of GLV, such that it has zero trace. And then type B and D. So this is the subalgebra of GLV. So this is sort of preserving. So this is going to be a symmetric, let me see, preserving a non-degenerate symmetric bilinear form. And then you have type C, which is it's the same, except instead of symmetric, you have skew symmetric. Okay, and then you have the exceptional, which don't belong to. So these are A, B, C, D, R families, and then you have the exceptionals, which don't belong to any family. Okay, so this is a quick review of the classification of Lie algebras. So now let me move on to simple Lie superalgebras. Okay, so it's you start out with so-called what they call superspace, which is a Z2 greater space, vector space, and it has a sort of super bracket, which is again a bilinear map from G cross G to G, which is compatible with the Z2 gradation. So it means that G0 bracket with G0 is land in G0, G0 bracket with G1 is supposed to land in G1. And it should satisfy. So this the following. So here below, X, Y, Z. So in our homogeneous elements, in G of degree, which I use absolute value to denote the degree, the Z2 degree. And so it's satisfying this super skew symmetry. Oops. X. Yeah, and then so and then you have this Jacobi, which is so minus 1, x and y, y, x and z. Okay, so then this is what a least superalgebra is, and simple means there's no non-trivial ideal. Okay, so then the note. Is that so G0 bar is the algebra, because when when the degree of x and y in this part here with this equals 0, then these are just the usual skew symmetry and Jacobi identity. And number 2 is that this G1 bar is a G0 bar module via it with a joint action. Yeah. Okay, so then let me give you also quickly just example as before. So this is a general linearly superalgebra. You take just instead of you take a vector space which is Z2 graded, and then so this grading Z2 grading provides GLV with a Z2 grading. So in degree 0 means that it preserves the grading, degree 1 means it swaps the grading. And then you define for homogeneous elements the super bracket, just like this. Okay, so this is defined only for homogeneous elements, but you extend this by linearity to all of G. So then this will be a least superalgebra. And of course, again, the same arguments as the GLV will act on. So V is the GLV module. Okay, so again, as before, so representations and representations of G and G modules, these are two interchangeable terms. And so, but in this talk, I will only consider Z2 graded modules such that the Z2 gradation is compatible with the Z2 gradation of G. Okay, so now let me give a sketch of the classification of the simple finite dimensional, simple complex D superalgebra. Okay, so below, so let me just recall again that I will always take a superspace, so a Z2 graded vector space. Of course, here it's possible that one of the spaces is 0. So V0 could be 0 or V1 could be 0. This is possible too. So so the classifications of the simple superalgebras are as follows. Number 1, this is the SLV. So this is the analogous to type 1 for the algebra. So these are X in GLV. Such that now instead of trace, you have to take something called super trace is 0. I mean, if you take trace, it's not going to be a subalgebra. So, but what's a super trace here? So for an element X of the form X0, X1, this doesn't matter what it is here. So then if the super trace X is just the trace of X0 minus the trace of X1. So then SLV is simple. This is not a quite correct statement. I mean, it's simple if the dimension of V0 and V1 are not the same. But if it's the same, then you see that the identity is also in there. You have to quotient out by that, and then it's simple. Okay, so I mean, SLV is always simple. So this is the type A. Okay, then so the second is this type OSP, which is type BCD. So here you take, so you have V, which is a, as I recall, it's a superspace. So we can take a so non-degenerate, so supersymmetric. So I'll explain what it means. Bilinear form on V. So this means that this bilinear form restricted to V0 bar is symmetric. And when you restrict to the odd part, it's skew symmetric. And yeah, I should, for completeness, I suppose I should also tell you what this is zero. Then you can then always P V. So this is by definition, so this subalgebra that you need this sign here. Is zero. So this is just the usual. So it's preserving this bilinear form, and this gives you type B, C, and D. I mean, this is I mean, what you see that in the case if you take if V1 is zero, for example, then this is just the orthogonal algebra. So, and if V0 is zero, then this gives you just the symplectic algebra C. So this is this certainly when you so remark here is that so if we take V0 bar or V1 bar equals zero, then we get so the algebras of type A, B, C, D. Okay. Okay, so these are all examples that are sort of expected. And so the next one is the type PQ. This is also expected, but there are no analogs in the classical setting. It's because so they appear when the dimension of the even space is the same as the dimension of space. So when the dimensions are the same, then there are a couple of things you can do. So type Q, so it's as follows. So we can take an isomorphism. So it's degree of reversing isomorphism of V. So swapping V0 and V1 bar. And then the Q, type Q Lie superalgebra is Q, I'm not sure it's QB, I'm not sure this is a standard notation, but this is a sort of subalgebra of GLV, so that it commutes, consisting of operators commuting, so so super commuting. I think it's actually commuting, so, but it doesn't matter. You send the same thing. Commuting with this isomorphism, this degree swapping isomorphism. You have to take probably also take either trace equals zero or all trace equals zero to get something simple. But essentially, this is how you get type Q. Okay, so then the type P. So this is also something that can only happen when the even dimension equals odd dimension. So in this case, when the dimensions are the same, we can take a bilinear form that pairs V0 bar and V1 bar non-degenerately. Okay, and then so V0 pair with V0 gives you zero, V1 pair itself also gives you zero. Then you take the subalgebra that preserves this pairing, and then you get this algebra PV. So to be precise, to get a simple, you probably need to take you need to quotient out maybe by the identity or something like this, or a trace. But anyhow, but this is essentially what you get, what P and Qs are. So you see that there is no classical analog because I cannot take the dimension of V0 or V1 equals 0, because then I get 0, so I get nothing. So therefore, this is something that's there for which there are no classical analogs for fully algebra. So then the other ones, so the other types. So another one. So this is also. So I think this PQ are also kind of expected, and people actually also have physicists knew about them for quite some time already before the classification by Katz. So then the other ones that physicists are probably not so aware of is the so-called Cartan series. So let me consider the classical picture. So for n, an integer, so we consider, so this Wn. This is the, oh, we just write probably this way. So this is the Lie algebra of first order differential operators with polynomial coefficients. So this is just vector fields, if you want, on Cn. So this is written something like Fi dxi f from 1 to n, and Fi are just polynomials. So of course, it turns out this is simple, but the problem, of course, this is infinite dimensional because these Fi's can be, it's a polynomials. So, but then, anyhow, this is something infinite dimensional, but still simple. Then you have the subalgebra of so-called divergence-free vector field. So this is the subalgebra of Wn consisting of differential operator with zero divergence. Okay, so this means divergence of D. If I write this is a D, and this is just a sum dFi, dxi, so divergence free. This is also in infinite dimensional. I should mention that. Okay, but then there are this Cartan series. There's also the Hamiltonian vector fields. So this is the subalgebra of Wn that preserves a symplectic form. So this is this is also infinite dimensional, but this is only possible when n is even. And then the complete series actually also includes something called the contact vector fields. Okay, but essentially, the Cartan types, Lie algebras, consists of those four infinite series. They are all infinite dimensional, I should say. Okay, but why are they relevant in the classification of simple Lie superalgebras, which are finite dimensional? Because there is there's an easy way to get a finite dimensional analog of these Lie algebras. Namely, so now we replace x1, xn by odd variables, zeta 1, zeta n. Then polynomials become, then this polynomial analog of that will be replaced. So it's replaced by the exterior algebra. And then this becomes finite dimensional. So then you get this Wn, which is the analog of Wn, so all polynomial vector fields. And then you have Sn, which is the analog of Sn, which is divergence-free vector field. And then you have Hn also, so which is an analog of Hn. K, the analog would still be infinite dimensional, so it doesn't work. But then there is still another one. What happens is there is another, so there exists, so a filtered deformation. Yeah, I should not use this term. So there exists a filtered, so these are all graded. You can just put degree zeta I to be 1, and then this gives you a grading of Wn, Sn, and Hn. So these are all graded. But then there exists a series, or it's a filtered Lie superalgebra, so-called Sn tilde, denoted by Sn tilde by Katz, such that so it's not graded, such that it has it's associate graded. So it has filtration such as associate graded is isomorphic to Sn. And this is only, and I mean this it turns out that yeah, I mean it's actually this is only, it works only when n is even. When n is odd, you can do the same thing, but then you get something, but then the algebra will be graded. So then it's the same thing as before. So when n is even, then you get something which is new. So this is the, so then you have then Wn, Sn, Hn, and Sn tilde. You have 4 more series. And then finally, this is number 5, I think, you have the exceptionals. So besides we have the exceptional Lie algebras, which I will not mention anymore. This is G2, F4. And the E series, you have also this, sorry, small rank. So with D2, 1, zeta. Zeta is so it's a parameter not equal to 0 minus 1. You have a G3, and you have something called 4. I will come back to those guys a little bit later. Yeah, I think that's okay. Right. Okay, so this is this actually. So the theorem of Katz is that so this is a complete list of finite dimensional simple the superalgebras over C. And this is the classification. This was so this is the final work was completed by Katz in 1977. So a little bit early, I think, for non-degenerate, so killing form. So this is by 3 physicists, Breitenberg, I think Schoenert, and now. So this work appeared a bit earlier. So they classified the simple Lie superalgebras which have a non-degenerate killing form. So I mean they have actually for this they have to actually how should I say? I mean it's certainly, I think the exceptionals. So the exceptionals D21 zeta, G3 and F4. These are non-trivial examples. But these 3, they do have non-degenerate killing form. So in order for them to classify it, they have to construct these superalgebras. And and they prove the existence of this. So existence of these exceptionals. So this is proved by these Rittenberg, Schoenert, and Nahm. But actually, they were conjectured to exist earlier by, so conjectured. to exist by Freund and Kaplansky in the early 70s. Okay, 76, I think. Okay, so this is a complete list of these finite dimensional simple Lie superalgebras. So I think then I want to move on to representation theory, but I think because so I want to mention about what is known about currently about the problem well, the status of these representations of Lie superalgebras. So, but it's I would not just know. The only thing I will just list it's just a list. So therefore, I will try to just show you the slides here. So without so I wrote this thing a little bit earlier. So I mentioned earlier I will talk about finite dimensional module category and also about category O. And so for finite dimensional module categories, so they have been studied since, intensively since classification, since Katz's 1977 paper. So the first problem that one asks, of course, is to classify finite dimensional irreducible modules. So this amounts to labeling these highest weights. So which highest weight give you finite dimensional irreducible modules? And this is a relatively easy problem, and this is solved already by Katz in this 1977 paper. Then the next question, natural question, is the computation of finite dimensional irreducible characters. This turns out to be a much more challenging problem. And there are many, many contributors. I'm sure with the list that I've listed here, I've missed at least 1,000. But so let me just probably the most important ones. So Victor Katz, of course, he started this out, and he also classified what's called he computed the characters of so-called typical modules. Then there are contributions by Saganova, by Penkov, and then so Saganova, Penkov from QN type A, and also Saganova also goes on with OSP. Chamonix to some from the exceptional types. And van der Joik for D2 and zeta. And then also there are different viewpoints provided by Brandon. So he really, I think one of his important contributions, he provided a new viewpoint to solving these irreducible character problems via Lustig's canonical basis. And that I think has enabled progress in this direction very much, especially for category O. Then there are different viewpoints were provided by Suicide, many examples, and also joint work with Rubin Zhang. And also I have done some work with Wang and also with Wang and Wang, and also this new viewpoint we provided in a 2004 paper, a joint paper with Wei-Chang Wang and Rubin Zhang. This were the idea of superduality, and also the conjecture of this equals category was first formulated. And so these are probably different viewpoints, and also there are others. I'm sure I just randomly list here, like the King and others, and physicists and his many co-authors. Bernstein, Leites, Shapovalov, they actually did this for this Cartan series for finite dimensional, and then also PN that's just completed just 5 years ago by Balagovich and nine others. So these include Saganova, Stropper, Letzte. I'm not sure I can recall them. I think, anyhow, so let me just stop here. So there are many other people who have contributed to this problem.
I have a question.
And so by now I should say that this problem is solved. So finite dimensional irreducible characters have been completely solved now.
Excuse me, Shun-Jen. Paul, do you have a question?
Is there a Chern-Wade construction of these representations? Basically, I'm interested if there's something different, getting these representations via holomorphic bundles.
No, there's no. I don't know. I don't think so. This is not for typical modules. I think there are some works in this direction here, but I didn't define typicality. But but I mean, generically, of course, the module is typical, but for those modules that are most interesting, these are atypical. And for those, there is no such.
So in the typical case, is there something different happening?
Yeah, I mean, it's actually when it's typical. I mean, the situation is actually very similar to. Okay, so what happens that? So in general, in a block, even in the finite-dimensional module category, in general, the block is not controlled by the Wang group, as for Lie algebra is the case. For Lie algebra, any block is controlled by the Wang group. But in the case of typical, it is. So that's what's separated. And also when it's atypical, then usually a block, any block will have infinitely many symbols. So they're not parameterized by the Wang group, and that's what's different. So I think that's the basic. Yeah. Okay. So let me move on to the situation in category O. I'll also be very, very brief. So the BG category with respect to a fixed Borel subalgebra. So this is a category of G module, which is by definition H semi-simple, finally generated over U of G, and also should be bounded above by finite many weights. So this is the usual definition. And the fundamental question here is the computation of the irreducible characters. So which I would know by L lambda, actually by L lambda with highest weight lambda minus. So I don't know whether this matters or not. I mean, because if I have time to give an example at the end, then this will matter. But if I don't have time, then this will not matter. Whether this says the highest weight is lambda or lambda minus 4. Rho is this usual. This is a usual shift by this half sum of positive roots. In this case, I mean, superalgebra needs a sum, but I mean, in any case. So I'll just go through this very quickly. So type A, this is solved, and essentially this is the characters are given by the so-called Brandon-Castandosi conjecture, and so this conjecture was proved by Lam and Wang and myself in 2015, and then Brandon, Loseth, and Webster in 2017 gave a graded version of that, and some parabolic version was established earlier by myself and Gao Lam. And the type BCD, this is solved by, in terms of so-called this icanonical basis of quantum symmetric pair. So this works of Bao and Wang and Bao. And it's also parabolic version exists earlier, so some journal with Lam and Wang. And then for type QN, actually, so category O for integral weights is at this moment, my understanding is still not known. But there are other blocks, so-called S weight. I don't want to go into details, and then also 1/2 integer weight. So these are provided. These are the characters were conjectured by, say, in some paper by a joint work with Kwong and Wang, and they were both proved by Brandon and Davidson later on, and so they are also related to some sort of canonical basis, or actually in one case it's even this Webster's orthodox basis. For type P, this is still open as far as I know. For Cartan types, in the Z-graded case, with respect to certain Borel, Saganova has a solution of this. And for the filter case, I think I don't know whether it's as far as I know, I don't think it's no at this moment. So then this remains the exceptional types. As far as I know, for F4, so PG category O, this is still open at this moment. And for D2 and Zeta and G3, so this is solved in a series of 4 papers. So there's 2 joined with Weichang Wang, and then 2 joined with Qiwei Chen and Luo Li. And I should know that there's actually, so for finite dimensional characters, actually, this works by Xiaomoni, also Van der Joik, and also I think also a student of Saganova's in their thesis, Matrosian, even not even quite recent actually. But a certain maximum probability category was also computed by Su and Zhang in 2016. I mean, they actually have more. They even have this rigidity of this Janssen module, parabolic modules. Okay, so this is the situation here.
Okay, well, we're all looking forward to hearing what you have to say about the representations of the exceptional Lie superalgebras. So please go ahead.
All right, thanks. Okay, so this is part 4. So it'll be about simple exceptional Lie superalgebras. So the first one, this is D2 on zeta. So this by G. So as I said, I've said earlier, so a Lie superalgebra, so G0 is going to be a Lie algebra and G1 is always a module of G0. So in this case, this is very easy. So it's a Lie algebra, it's a direct sum of 3 copies of SL2. And G1 bar is just the tensor product of the natural representation. And I mean, and how the only thing I'd have to tell you how G1, how this thing works. But you see, this is really, I mean, this is actually because the bracket is symmetric here, so you don't have to find a map from symmetric square. And I'm pretty sure you know how to do this because the symmetric square of the natural representation, I mean, it contains, I mean, it's exactly the adjoint representation. So therefore, you can figure out the bracket here. So the one parameter comes in because of the choice of this data that you can choose from symmetric square C2 into the adjoint representation. So there is always a scalar multiple you can choose. And I mean, but I mean, it turns out that so I mean, in this, of course, because there are 3 copies, there should be 3 parameters, you could say, but you can show that eventually there's only 1 parameter left there. The rest, they're all isomorphic in a certain way. So this, we write down even, so what does it mean? The roots here and the even roots and odd roots. So first of all, so let me denote by delta, epsilon 1, epsilon 2. So these are the fundamental weights for each copy of this SL2. Then the bilinear form that one defines is defined as follows. So this is where this data comes in, this parameter. So I should say, so then what I didn't write down is an automatically 0. So delta with epsilon I is 0, for example. So then we write down so you have the roots here. And this is the roots. So you have the even roots. So these are the roots correspond to even subspaces. So this is then 2 delta positive 2 epsilon 1, epsilon 2. So this is a copy of SL2, SL2, SL2. And then the odd roots, odd positive roots. So this is the tensor product of natural representation. And here again, so this in this case is still okay. So positive roots. Sorry. What else do I need? So if you want, the Stinken diagram is as follows. So this is I mean, there are many different choices, but this is the one that's the most used most often. So this here, so this stands for an odd isotropic root. So you can check that these 3 roots will generate all the positive roots. Okay. Okay, so then here I should also write in the future lambda as a weight. Simply write it as lambda 0, lambda 1, lambda 2. So later examples.
Can I ask a question now?
Yeah, sure.
So why does this work with 3 copies and not with another number of copies of SL2?
Yeah, because I mean, it's yeah, I mean, it has to be simple. I mean, it has to satisfy. Okay, I mean, I didn't. I mean, of course, you can always define it this way, but it has to satisfy the Jacobi identity as well, when all 3 of them are odd. So what I've written down here, it's only basically only will satisfy all Jacobi identity except for this one. When you have them. When X, Y, Z are all odd, then this has to be satisfied as well. And so in general, this in general this is not true. This will not work. Okay. And also, of course, you can always take 0, but it's not simple. Yeah. So yeah. Okay, so this is the first one, and the second one I will also talk about is G3. So this indeed it has G2 in it, so it's even part. So this is a SL2 and a copy of the exceptional Lie algebra G2. And G1 bar, so this is natural representation of SL2 with the 7-dimensional non-trivial representation, irreducible non-trivial representation of G2. And yeah, I'm pretty sure I will not go into much detail of this, but let me just, yeah, just in case if I really get into examples later on, let me write this thing down. And then the thinking diagram looks like this. So this here is G2, and this is an odd isotropic root. Yeah, I mean this. So I'm not sure I want to write down all the roots here, but in any case, so notation for later. So delta, omega 1, omega 2, sort of fundamental weights for SL2 and G2. Okay, so this is the one I will use, this notation. And lambda, so I will also write something like this. And I'll also use this notation for later on. So I should also mention that, so lambda is integral. But if you want definition, if lambda I are all in Z, and the same thing. For I, and if otherwise we'll call this non-integral. Okay, so then, okay, just for completeness, even though we don't have the solution for this case, but let me also quickly tell you what F4 is. So here, this is SL2, SL7. And G1, this is always natural representation and spin representation. And yeah, I will not tell you the rules, but I mean, from this you can easily figure out. So, but this is, I mean, there is no F4 in this picture at all. And the reason it's called F4 by Katz is because in one of his Ding diagram, it looks like an F4. It's if I have to be a little bit careful. What I think it's something like. I think it's something like this. So it's a 2, of course. No, sorry. I think like this. I mean, of course, this part, this is a SO7, and then there's not. Oh, that's true. So, but I mean, it's of course, it's really, it's not related to F4 at all. So, but there you go. So this, okay. So now let me move to representation theory. Okay, so so below I will. So below. So let me have notations that I need. So here lambda is an element of dual, and then I will denote by m lambda. This is the Wärme of highest weight. So I will shift by rho. So this rho is this half super sum of positive roots. So super sum means it has a sign involved for outputs. And then I will use L lambda. So this is the irreducible. And then I will also need this tilting module. So we have in this shifted notation, this becomes a little bit easier. So we have this, so tilting modules has a flag. So this is by tilting, I do mean irreducible of high speed lambda. So tilting module T lambda has a flag. Wärme flag, and also dual Wärme flag, of course. And we have this Ringel type duality. So the multiplicity T lambda M mu. So if I use this shifted notation, it becomes M minus mu L minus lambda. Okay, so so from this here, it means that it follows that so this computing the character of L lambda is equivalent to computing the character of T lambda. Okay, so this, we only need to compute this multiplicity here. Okay, so the method to compute, so the method to compute the character of T lambda is as follows. So actually I should say that in these cases, for G equals D2 and zeta, and G3, so it's quite elementary. So it's as follows. So before I do that, so I make first two. So we apply. So translation functor. So we call this epsilon to a tilting module T mu with known character. Okay, then there are two observations. So the first one is that after you apply this translation function to this T mu, if you know the character of T mu, then after applying the translation function, the character of this is easy to compute, because I mean we applied translation function to Wang module on the character, so therefore it's easy to compute. And T and tilde module as a flat family modules. And the other thing is that I know that because T is tilde module, you apply a translation function to tilde module, this still is a direct sum of tilde modules. I mean, maybe I mean, for people who know, probably this is quite simple. For people who haven't seen this, maybe this looks a little bit more mysterious. But at the end, I will do one computation, one example. So I think this will be clear from there. So it means like this. So if for example T lambda is what we want to compute, or rather character T lambda to compute. And we know, so translation function to T mu equals T lambda plus other tilde modules. So this is quite I mean the ideal situation is that we can choose mu and this translation function so carefully that after applying translation function, we know it's indecomposable. Then now we get this. But then I just mentioned earlier that this is easy to compute. The character of it is easy to compute. Sorry. Character of this is easy to compute. So this then implies that it's problem solved. But this is, of course, it looks like a miraculous thing. I mean, still and even if it's true, you still have to prove it's indecomposable. So, I mean, if this is really true, but I mean, it turns out that actually in these cases, in G3, very often, so mu and this translation function can be chosen. So that indeed is indecomposable. So then this is, but there are, of course, still several cases where you know it's not indecomposable. And then in this case, you have to really find different methods. So for the cases when this is not possible, so we need, so we direct, so different arguments. So it's case by case argument. So that's roughly how this is done. I mean, it's a very naive method is also, but at the same time, it's also very computational. I mean, here I think the important thing is that, I mean, because you can vary mu, you can choose different mu. You can also choose different translation functors. So you can tensor with different kind of modules and take different projections to blocks. And here it's for so this is where Mathematica is useful. G3, so we use Mathematica. I mean, the reason is really because this gives you many possibility to experiment with different mu's and different translation functors, different modules. And so yeah, I mean, the upshot is that, I mean, for these two exceptionals, this naive method really works. And I mean, I think it's also, I don't know, we don't know of any other method because, I mean, for this series like type A, OSP, or Q, you can relate them to canonical basis in a certain way. But here, for those, we just don't know how to do it. Okay, so there is one lemma which is, I'm not sure how much time I have. Yeah, there's one lemma which is quite crucial for this calculation. So I want to state this lemma. This really is, I will not state the full lemma, but certainly part of it, so give an idea what goes into showing this epsilon t mu is indecomposable. So let me state this lemma. Suppose lambda is any highest weight, and alpha and alpha I are, so these are even roots, and beta and gamma are isotropic roots. This means beta equals gamma 0. And so let W suppose is as alpha k. So it's now made in the Wang group. And so one statement goes like this. So suppose lambda beta, suppose lambda beta is 0, then you know that m lambda minus beta must appear. And also the other statement is suppose lambda alpha check, so this is the even root, is an integer not equal to 0, or half integer, sorry, and this is the case alpha over 2. It's just a little bit technical, but this unfortunately is for superalgebra, this is needed. Then you can show that T lambda, so in the flag, so M of S alpha lambda must appear in the flag. And then there's other versions. Let me just list another one. So beta gamma is also 0, and beta is not greater than gamma. Then you can go 2 steps down. And then there's a Wang group version. So certain conditions, so I will not say the condition, but you can eventually get something like this. So I mean, and why this is so useful in this particular case is that because in many cases after after you apply a translation functor, it turns out that the multiplicity is always 1. So then, but then if you have this lemma, then this tells you that there cannot be anything else. So this is why this particular lemma is actually very, very powerful for these two cases. And so this way you can really so with this lemma you can find you can compute all the characters in the integral case, and but then you can also solve this problem for the non-integral case. Yeah, I'm not sure. I want to. I probably should state this somehow. Yeah, I think it's a little bit complicated. So let me just try to state this lemma here. So I think this is, so don't worry about this. Yeah, okay. So this is I think that's what I wrote earlier. So I would just go through this quickly. So I mean, so for a non-integral case, so what we need to do is first to classify. We classify according to this integral of algebra. Integral of algebra is defined in the same way as for the algebras. So in general, these atypical non-integral blocks are not always determined by the integral of algebras. Of course, by Lie algebra it is, but of course these superalgebras cannot be because of this atypical phenomenon. But but for this non-integral Weyl group cases, for this non-integral block cases, so for G equals D2 zeta, there are the following cases. So I said here it's enough to manage to consider the atypical blocks. This is because there is, for typical blocks, you can prove some equivalence of category between typical blocks of Lie superalgebras to certain blocks of Lie algebras. So therefore, it's really enough to consider atypical blocks. I mentioned earlier that in the case of typical blocks, I mean, the blocks, the simples are parameterized by the Weyl group. So it's just like in the algebra case. So this is no coincidence, and indeed there one can establish some kind of equivalence of category in these cases. So this is done for D21 zeta follows from work by Gorelick. For G3, it almost always follows from Gorelick but I mean there is a special case that doesn't follow from her work, but I mean we can prove a similar version, so an analogous version. So for typical cases it's settled, so we don't have to worry about that. For atypical blocks, then for G equals D2 zeta, it goes as follows. So so the Weyl group here is 3 copies of so you have SL2, SL2, SL2 as G0. So each one of them has a Z2 as its Weyl group. So therefore you have 3 copies of Z2 as a Weyl group. So in the case when the W lambda, when the integral Weyl group is just the identity, then you can prove that this block is always equivalent to the principal block of the general linear Lie superalgebra of super rank 1, 1, GL11. Okay. When W lambda integral Weyl group is Z2, then this block you can prove is always equivalent to the principal block of GL21, but not always as highest weight categories. Okay, but I mean well here the reason is because GL21 has different Borels, subalgebras, and in contrast to Lie algebras, the highest weight category with respect to different Borels, they are not equivalent. They're of course equivalent as category, but not as highest weight category. So therefore, this is why, as I mentioned here, not as highest weight categories. And then in the case of W lambda is Z2 cross Z2, then the blocks there are many blocks. There are different blocks parameterized by a positive integer. And it's not all of these blocks can be equivalent, but conjecturally, I think most of them are indeed equivalent. There are some special cases where they are probably where I think they are not equivalent. But I should say that so in these cases, in this W lambda is E and W lambda equals Z2. So you have really a reduction of to integral blocks of other Lie superalgebras. But in W lambda equals Z2 cross Z2, you can show that these blocks are not equivalent to integral blocks of other simple Lie algebras. So this is the case for G equals D2 zeta. And unfortunately, the case of G3 is even more complicated. But I mean, actually, I think it's complicated, but I think the answer that we gave is still well organized in a certain way. So in this case, remember G0 is SL2 and a copy of G2. So the Weyl group here is the Weyl group of even parts. So this is for SL2, it's Z2. And for G2, there's the Weyl group of G2, which is the dihedral group. I think it's 12 elements. So again, we first we organize these blocks according to the integral Wang groups. So in the case, so these are all the cases that can appear. It's either the trivial group, it's either the Z2, or it's the Klein full group, or 3 copies of Z2, or it could be S3, or it could be just the Wang group of the dihedral groups in 12 elements. So in the first case, it's again, so when it's the integral Wang group is trivial. In this case, again, you can show that they're all equivalent, and they're all equivalent to the principal block of the least superalgebra GL11. When it's Z2, then there are already things are already different. So it could be equivalent to the principal block of GL21, or it could be equivalent to. So this is the principal block of SL2, direct sum the principal block of GL11, or it could be equivalent to a block of OSP32, but in this case you can show this mu is not an integral weight. So this OSP is already also a least superalgebra of a small rank. And then so when it's the Klein group, then I mean the situation is even more complicated. So then it could be the simplest case is when it's equal to an integral block of OSP32. And then there are other non-equivalent families parameterized by Z. And then with W lambda is this, and it's a family parameterized by 3Z. I should say that from looking at the characters, we have all the characters, we can compare all the characters. It's very suggesting that most of these blocks should be equivalent, but some of them cannot, as we know. Okay, it's almost, and then finally is, so when it's S3, then this is also these are the answers here, and yeah, I mean so there are various. Yeah, it looks like if it's a Lie algebra, the situation is of course much easier. Then the integral Wang group would determine everything already. But for these superalgebra, you can see, I mean, this is the picture is indeed quite complicated. So it's this, but in any case, I think we can also get the irreducible characters of all of any tilting modules of arbitrary highest weight for G3 and D21 zeta. I mean, there are a couple of minutes. I mean, if you want, I can do one simple calculation, or let me see. So let me do this. Okay, so let me. This is a very naive calculation here. So let me take D21 zeta. It's still a little bit easier. G. So here, let me just recall the roots here. So you have plus or minus 2 delta, plus or minus 2 epsilon 1, plus or minus 2 epsilon 2, so even roots. And then you have also plus or minus delta, plus or minus epsilon 1, plus or minus epsilon 2. Okay, so these are all the roots of D21 zeta. So let's consider shifted weight, so lambda. Let's take, for example, minus 2, 0, and 0. So then you can actually I should say the character will the plot certainly depend on zeta as well. So let's take the case, simplest case, zeta is irrational. This is somehow the most generic case and the simplest case. So then you can, if you take lambda, you take inner product with delta plus or minus epsilon 1 plus or minus epsilon 2, then you will see that, well, this is 0 and 0, so then you get just minus 2, so 2, 1 plus zeta. Because zeta is not equal to, because I mean, zeta is not equal to minus 1, and so this is not equal to 0. So what this means, this calculation means that because these are all the isotropic roots, this means that lambda is typical. But this weight, of course, with respect to the Wang group, is also anti-dominant. So this means that T lambda is just M lambda. Okay, let's suppose we want to compute t of 0, 0, 0. So this is already, this is not typical. Because I mean 0, 0, 0, because 0 is the inner product, you take inner product with any is 0. Okay. So so how do we compute this character? So we tensor this with the adjoint representation, and then we project to the block 0, 0, 0. So this means that you're really just taking the Gamma module. Sorry, -2 of course. So it's just the Gamma module tensor the adjoint representation, and then we project. So this Gamma module tensor with this adjoint representation, so we get a module with Gamma flag. So it has a Gamma flag. And they are precisely, these elements are just -2, 0, 0 plus, so this appears 3 times because the cut-down is 3-dimensional, plus -2, 0, 0, adding alpha. Alpha is order roots, okay? But now you want to, but I mean, not all of them are relevant because you only want to take the one which are in the same block as O. So the weights in O, the highest weights in O, I mean O 0, 0, 0, it's quite easy to check. So here the statement is that yeah, so L mu is in O nu if and only if nu is equal to, so it's element of W nu and nu plus K beta, where beta is an isotropic root, and nu beta equals 0. I mean, this looks strange. I mean, but it's really not very difficult to compute. So this is a linkage in this block. From this here, you can quite easily shown that actually, if you project this, sorry. If you take this guy, then you get a module with this Gamma flag, with following Gamma flag. So this is plus minus 1, so these are 5, these are 4 terms. And actually, the lemma will tell you that, so this must be equals to T 0, 0, 0 plus potentially something else. But the lemma tells you that, all these, that tells you that T 0, 0, 0, M minus 1 plus or minus 1 plus or minus 1, it has to be greater than 0. So you know that this is indecomposable. So therefore, this is exactly T 0, 0, 0. So this is one of those cases where you can see that when you do a translation, then this is indecomposable. But this of course is already, this is not a complete trivial calculation already, because this is not, how should I say? Just offhand, if you were to compute the character of T000, this is not, it's not something, this could be much longer, so it's in principle. But this calculation here actually shows that this is just a Taylor module. So that's one of the cases where, so this lemma tells you that all these terms have to appear. So actually, this is the one where you have this is indeed indecomposable. So I think I will stop. Thank you very much.
Thank you. Ruben.
So yes. It looks like the method works for F4 as well. What stops you from doing that? Too difficult?
You mean in general for F4?
No, for F4.
I'm saying F4.
Clearly, it's being under consideration. But I can tell what's stopping me right now, because you see, because of the Cauchy polynomial SO7. You see, in those cases of D21 zeta and also for G3, all these Cauchy polynomials, so for G2, SL2, they are monomials. So the multiplicity is 1. SO7 is not. So when you do the translation functions, you need to find, I mean, I only have a lemma that tells me the multiplicity is greater than 0. I don't have the lemma that tells me it's 2 or 3. And that's what's stopping me at this moment. I think it makes sense, right?
Yeah.
So is there a Cauchy type theory for the superalgebra itself, or do you just rely on?
In general, no. I mean, for those guys, it's not. I mean, you have for type A, that's the previous picture where you can relate them. I mean, so these you can define on certain space of quantum group modules. You can define so where you have a canonical basis, and it turns out that these canonical bases, they will actually determine the characters of GLMN. But in general, it's just not true. I mean, the only other case that I know is in the case of OSP, where you replace the quantum group by quantum symmetric pair, or by QN for Q. It seems like there should be also something like that. But so you have to. But this case, I think you have to the original conjecture by Brandon on type Q and integral weight. For character, you just for characters of integral weight, it turns out to be wrong. So it's because I mean, some calculation by a Japanese Tsushioka shows that the basis that Brandon conjecture these characters should be related to, they don't have positivity, so they cannot be. They cannot give you this. But it seems like there should be. I mean, it should be related to some other kind of basis. And for Q, it turns out in the half integer case, you can relate them to so-called this Webster's orthodox basis. But then Webster's orthodox basis, I'm not sure today whether there's an algorithm to compute them. So you could argue that that may not be a solution to the problem as well. So in general, the answer is no. So it's just.
Are there any other questions? Yeah, I see a hand raised in the room. Is that Geordie? Yeah, go ahead.
Can you hear me, Jordan? Can you hear me?
We can just hear you, but you could always walk up to the microphone. Yeah, maybe that's better.
I feel like I'm going to make an announcement. I'm just wondering if there's something like Janssen filtration in this setting.
I think Rubin probably knows better, right? No, but I think Rubin has he wrote 2 papers actually. I think type A and also exceptional types for parabolic gamma module. But in general, I think the answer is I don't know. I don't know. Maybe Rubin knows better. Besides those cases, Rubin, do you know any other cases besides the ones that you've considered?
No. But you can set up the problem, but we don't know what the Janssen filtrations look like, apart from the cases, there's exceptional cases, like all these cases Shun-Jen was talking about, including F4, or we could do F4 as well. But then we could also do type A. Janssen filtration.
But in those cases, these are the maximal parabolic, right?
Yes, for the mark, yeah, that's the maximum parabolic.
So in general, I don't think anything is no in this direction.
Okay, well, if there are no more questions, then let's thank Shun-Jen again, and hope that someday soon we'll be able to invite him to visit us in Sydney in person.
Yeah, I also hope that someday you can come to Taiwan, so hopefully soon.
Yeah. That would be nice.
Thank you.
Thank you.